Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm going to cover a topic that I seem to get questions about a lot, and it's how I go around and make disks for various systems that I work on. In this video, I'm going to be giving my PC that I usually use to do this task, which is this computer right here, an upgrade so I can read and write more disk types than I can in this machine. So, without further ado, let's get right to it. If you're into retro computers, and you probably are if you're watching this channel, one of the most difficult things about using these old computers is the fact that the disks that are used to store programs and load games and stuff like that can be very difficult to get your hands on. Now, you might be lucky and have acquired an old computer, or maybe you already had yours from when you were a youth, that still has all the floppy disks and they work. Well, what if you want to download a piece of software off the internet and then use it on your old computer, and that means you have to put it onto a disk? Or you could potentially be buying an old computer, whether it be a DOS PC or a lot of other computers that use floppy disks, and it didn't even come with any disks. And of course, if you had that computer when you were young, all those disks are gone, so now you have no way to use the computer. Now, I wish I could tell you that there was one machine you could set up or something you could buy that could read and write every single disk format super easily. Unfortunately, that's just not the case. It's a little bit more complicated than that. Now, there exists commercial disk archiving systems like this here, the CryoFlux, and there's an open source alternative called the Grease Weasel, plus I think there's something called the Zoom Floppy, and are specifically designed to hook up to a modern computer and allow you to archive, basically read in the data off a disk onto a modern computer, a Mac, Windows, or Linux PC. Typically, the data from these types of devices is actually saved to something called a stream file, which actually records the actual magnetic flux information that's on the disk, well, a digital version of it, into a large file on your computer that's basically an exact replica of the disk. These things are great if you're trying to recover disks that are partially bad or they have copy protection, things like that. And it is possible to take that stream file and then reverse it, basically write that back onto a physical disk, and that absolutely does work with these. You start to run into problems with these disk archival systems when you're trying to write a disk image you download off the internet back onto a disk, because those image files are never in the stream format that these things natively work in. They're usually some other format designed for use with emulators. I could probably make a whole series of videos on using these archival systems for reading and writing disks, and it's really beyond the scope of this video. What I'm going to be talking about in this video is using a PC, as in a DOS PC, to read and write disks of many different types of computer systems. First, though, we have to cover a few basics about the way disks are actually written by computers. Because I'm not good with fancy graphics programs like David Murray on 8-Bit Guy, I'm going to be drawing some things on a Post-it note for all to see. If you want to use an IBM PC compatible machine to read and write disk images, like I predominantly do on this channel, you have to be aware of the disk encoding or the floppy disk encoding method used to make the disks. A disk is really just like a tape, like an audio cassette, and information on an audio cassette or any magnetic media device is stored in the analog domain. So if you're going to store digital information on something that's analog, you need an encoding method to convert that digital signal into an analog one. And then when you read that signal back off the disk, you have to reverse that process to convert that analog signal on the media back into a digital signal. If you ever used a modem back in the day to dial up to the internet, this was no different, because of course, a modem is connected to an analog phone line that's designed for carrying a voice sound signal, and it has to take a digital signal or digital data and encode that into a way that can be sent over the analog line and then converted back to digital on the other end. And actually, here's a little bit of interesting tidbit about modems. The technology of what a modem did got better and better over the years, which is why early modems were 110 or 300 bits per second and used a very simple encoding scheme to send the data over the analog line. Well, phone lines didn't really get better quality over the years. I mean, they did a little bit, but generally the amount of bandwidth available on an analog phone line was the same throughout history. And what enabled the modem to hit 56,000 bits per second was much more advanced encoding techniques that were developed down the road. Anyhow, let's get back to the topic of disks. There are predominantly three types of encoding methods that are used on floppy disks, especially 5¼ discs like this. There's FM or frequency modulation, MFM or modified frequency modulation, and GCR. I don't remember what GCR stands for off the top of my head, but it is a different format than these other two. There is also an other type. I put down other. Typically systems that use this other encoding method are very old systems from like the mid-70s or early 70s. And they are doing that because there was no off-the-shelf disk controller ICs they could buy that would use one of the standard formats. Therefore, they kind of went their own way. And those types of formats can really only be read and written using the actual disk controller itself on that machine, or using something like a disk archival system, which read and writes the actual flux information right off the magnetic media. Luckily, those types of disks are pretty rare, and generally everything else falls into one of these three formats. Now, when it comes to IBM PCs and reading and writing disks, the disk controller that's on these types of controllers, now this is one that TechSelect made here, but there are many that are all compatible with each other on the IBM PC, and these can read and write in the FM and the MFM format only. Systems that use the GCR format, which means you cannot read and write those disks, are things like the Apple II, all the Commodore disk formats, well, at least the 5¼ ones, and the Macintosh 800K disks, which are written on 3.5" disks. There are other systems as well that may use GCR, and those disks will not be read and writable at all in this system with any type of regular disk controller card that is compatible with like the original IBM PC disk controller that was found in the original IBM 5150. The FM encoding scheme is also known as single density. So if you see disks that say single density, single-sided, that's going to be using the FM encoding scheme. MFM, which came later, increases the amount of storage capacity on a disk, and it's called double density. Incidentally, the high density disk format, which you may know for things like 3.5" disks like this HD one here, and also 5¼ disks, uses MFM encoding. The fact that it's high density has nothing to do with the encoding method. It has more to do with the data rate, and in some cases, the number of tracks on the disk. I'll talk about that more in a second. Now, I can probably hear you asking, why did Apple and Commodore go with the GCR format instead of using one of the standard ones? Well, I think the answer is twofold. GCR is more efficient at storing data on the disk than FM. So you just get more on your disk. Even though it's the same physical disk, you're able to store more data on it. In addition, disk controller chips, like the one that's found on this card right here, were probably pretty expensive. And if you look at the Apple II disk controller card, it's a pretty ingenious design where all of the complexity of reading and writing the disk is actually handled by the CPU of the computer and not a dedicated controller chip like on cards like this. So as a way to save money, Woz probably decided that it just wasn't even worth using a controller chip, and he just did it himself, and he did it in a very elegant way that offered more storage capacity as well. Now, luckily for enthusiasts like us, most systems use FM or MFM encoding because they're just using an off-the-shelf controller IC, which was a lot easier than designing your own system entirely from scratch. And that's a great thing, because that means a disk controller card just like this one, which is actually manufactured in 2022, can read and write all the FM and MFM encoded disks on a regular DOS PC using a piece of software like IMD or ImageDisk by Dave Dunfield. I will talk about IMD a little bit more coming up, but for now, there's some more differences on disk formats that we need to talk about before we get to actually testing some of this stuff out on a real computer. Unfortunately, it's not just the encoding method of the data on the disk that you have to worry about if you're going to try to make disks. Remember, I mentioned that this is just a plastic disk with magnetic material on it. There is no actual physical layout of the way the data needs to be encoded on this disk. It's purely up to the way the disk drive is designed and the way that the computer writes the data onto it. There are various physical characteristics of the original disk drive in the computer you're trying to make a disk for that you have to match to be able to read and write disks from that particular computer. On 5¼ disk drives, there are generally 3 types of physical ways to write the track data onto the disk. Very common on older machines are 48 track per inch disk drives, and those typically write 35 or 40 tracks on a disk. The difference there with those extra 5 tracks is simply the head moves further on the 40 track drives than it did on the 35 track drives. As far as I'm aware, Haardt Associates invented the 5¼ disk drive format, the physical characteristics of it, and their original mechanism, the SA400, was 48 tracks per inch. Most early systems use 48 track per inch disk drives. The Apple II does, even with its GCR encoding, as does the Commodore, the original IBM PC, and many other types of disk drives that have that large full height 5¼ inch disk drive are using 48 track per inch mechanisms. That means if the encoding method is FM or MFM, like we talked about already, then a 48 track per inch drive hooked up to an IBM PC can read and write those types of disks properly. Now, in order to allow more data to be stored on disks using the same encoding method, the drive manufacturers started creating 96 track per inch drives, which basically doubled the number of tracks from 40 to 80 on the same physical media. So even though this is a regular double density disk here, and you think this is only good for 40 tracks of data, it can actually be used in, well, what I think is called a quad density drive, which writes 80 tracks onto this disk. And that effectively doubles the storage capacity on the same physical media. Systems that use these drives typically got about 720K of storage on one disk, a double-sided disk, using MFM encoding. When, of course, if you remember that typical MFM encoding on a double-density 40-track disk results in about 360K of storage. Unfortunately, there is actually one more type of physical way to write tracks onto a disk, and it is 100 tracks per inch versus 96. It still results in the same amount of storage space, but the difference between 100 tracks per inch and 96 is large enough that if you try to read a disk that was written on the other type of mechanism, some of the tracks are going to read, but then it's going to start to get more offset as the head moves across the disk, and it's just not going to work properly. Systems that used 100 tracks per inch are definitely a little less common, and 96 and 48 are by far the most common, but I've still run across some disks that are written on 100 tracks per inch, and you'll figure that out if you try to read one on a 96 tracks per inch drive when some of the tracks just start to completely not read at all properly. Incidentally, the 48 track per inch drives write down a thicker track onto the magnetic media than the 96 track per inch drives. So if you try to read a 48 track per inch disk in a 96 track per inch disk drive, like a 5¼ inch high density drive on a PC, it probably is going to read properly, because what happens is the operating system will double step the heads. So even though it's an 80 track drive, it's going to read 40 tracks by double stepping. But if you try to write information back onto the disk, what gets written down onto the disk is much thinner than the original wide track that was written by the original drive. So while it might read back okay on the high density or the 80 track drive, if you put that disk back in the original 48 track per inch drive, which has a wider head or track width, it's probably going to read both the original signal that was written with the wider track and the new thinner track. There'll be crosstalk. So really, ideally, if you're going to be working with disks a lot like I do, you really want to stick to the 48 track per inch drive if the original disks or the original machine has that type of drive, or 96 for the same, or of course 100. You have to use 100, otherwise it's just not going to be compatible. I haven't really touched on 3½ inch disks, but basically they're always 80 tracks. The only difference in high density and double density is the actual data rate that's written onto these. These are generally always written in MFM, although maybe FM ones exist out there, but it's MFM encoding, and then there's two different data rates, 250 kilobits per second and 500 kilobits per second. Now, and actually, this data rate difference also exists in the 5¼ inch world as well. And generally, everything that is considered double density or single density, so FM or MFM, single density or double density, is always going to be 250 kilobits per second. Now, it is actually possible to use 500 kilobits per second on a 5¼ inch disk, and that is the high density disk format. And the reason why that exists is because IBM took the original 8-inch disk drive and they shrunk it down to 5¼ inch size. All of the physical characteristics of the 8-inch drive, the speed of the disk spinning, the data rate it writes at, everything was just shrunken down, and that is what the high density disk format is. It's a little bit of a hack on the original 5¼ inch disk standard, and honestly it kind of confuses things, and I wish IBM hadn't done it. But they obviously wanted to be able to increase the storage of those 5¼ inch disks, and just taking all of the physical characteristics of the 8-inch disk and shrinking it down was how they accomplished that. Otherwise, if it's MFM or FM encoding on a 5¼ inch disk, it is written at 250 kilobits per second. Now that brings me to the question of RPM, or revolutions per minute. The original 5¼ inch disk standard ran at 300 RPM. That's what it runs at. 3½ inch disks also run at 300 RPM. There are some weird outliers, like the Macintosh 800K format has like variable speed. And there are some 8-inch disk drives like the disk drives that HP used on their HP 150. Those run at 600 RPM. But generally, if it's FM or MFM encoding on a 5¼ inch or a 3.5-inch disk, it's running at 300 RPM. We run into issues with that high-density disk drive that IBM designed, again, for the original 5170. Those drives typically are configured to run at 360 RPM because that is what 8-inch disk drives run at, and IBM, like I said, shrunk down the format. That poses a problem if you try to read a disk on one of those drives that was written on a 300 RPM, 250 kilobits per second drive, like a regular double density drive. Reading and writing that disk is going to be at the wrong data rate because the disk is physically spinning faster. So there's actually a third data rate that these types of controllers support, the ones that were designed later in use on the IBM PC and later, and it's 300 kilobits per second. Basically, 300 kilobits per second plus a disk drive spinning at 360 RPM, reading and writing a disk that was written on an older drive that runs at 250 means it's actually going to line up and work. Unfortunately, that complicates things if you download a disk image of a double density disk that was made on a high density disk drive on a PC. Essentially, the disk image is going to want to write back to the physical disk at 300 kilobits per second. But if you're writing a double density disk back to a double density disk on a proper 300 RPM, 48 track per inch drive, it needs to be written at 250 kilobits per second or it's not going to work. Hopefully with all of that talking I just did, that gives you a little bit of information about all the different physical characteristics and disk encoding methods used on disks to help you kind of have a base knowledge that will allow you to use some of the tools I'm going to be talking about coming up in the rest of this video. If you're looking to get a machine set up that will allow you to make and read and write disks for all sorts of different systems, let's talk about the things you're going to need to make that happen. The first thing you're going to need, of course, are physical disk drives. What this is a double-sided 48 track per inch disk drive. It runs at 300 RPM. It's made by Toshiba. It would be basically what you would think of as a regular 360K PC disk drive. It uses the normal edge connector, which is typical for the 5¼ inch drives. It's a typical Haardt pinout, and this is pretty much just a bog standard drive. Next up, I have a TIAC 96 track per inch disk drive here, typically known as a standard high density disk drive from a PC AT. Since this is a 96 track per inch drive, it writes with a thinner track width, which is appropriate if you're going to be reading and writing any disks that come from a machine that also use a 96 track per inch drive. And lastly, I have this disk drive right here. What's special about this particular disk drive, while it looks like a normal full height double-sided drive, is this is actually a Tandon TM100-4M. And there's a very special thing about these particular 4M drives. If we flip down the lid here and you take a look at the inside, it says 100 track per inch. Yes, this is actually a 100 track per inch double-sided disk drive. Pretty rare thing in the grand scheme of things, because as I mentioned, 100 TPI drives are just quite rare. The drive has a standard Haardt edge connector just like the other drive, so it can be used in any PC just like the other two drives I just showed. Now when we look at these three drives, this is the 48 track per inch drive, this is the 100 track per inch drive, and this is the newer 96 track per inch high density disk drive. These two drives are designed only to use 250 kilobits per second as the data rate, while this high density drive of course supports 500 kilobits per second and 250. And the 500 kilobits per second, as I mentioned, is that compatibility with the original 8-inch drives, which all used 500 kilobits per second. And then the fourth type of disk drive, of course, is this, which is just a normal 3.5-inch drive. This is a regular 1.44 meg high density Mitsumi drive. Not much to say about this. All these drives are 80 tracks, so they're all pretty much compatible with each other. It's 300 RPM and it supports 250 kilobits per second and 500 kilobits per second data rate. So yeah, you can pretty much read and write all 3.5-inch disks with this. Oh, I do want to add that there are other types of 3-inch disk drives. This type of mechanism on this was, I think, invented by Sony, and that's pretty much what became the standard. There were other types early on, like the Amstrads use. Those, of course, are physically different than this, although I'm quite sure that they just use MFM or FM encoding as well. So the actual encoding method is the same, and I think even the signaling is the same, the Haardt type signaling. The connector may be different, but the actual digital signals are the same. So I would imagine you could probably plug one of these drives into your Amstrad, make a disk image on the PC onto a regular 3.5-inch drive, and then it would work on your Amstrad. Of course, it wouldn't physically fit in the computer because the size of the drive is a little bit different. I'm not really going to do much more talking about these types of drives, and let's get back to the 5.25-inch drives, which are the more complicated and harder to figure out format. So if you're looking to build up a DOS computer to be reading and writing disks of these other types of computers, you got to think about what type of disks you're going to be trying to make. Most likely, you're probably going to want yourself a 48 track per inch disk drive like this, a double-sided one. That's going to give you compatibility with all the systems that use single and double-sided 48 track per inch drives. Of course, if they're using FM and MFM encoding, which is most of them. Of course, it goes without saying that 3.5-inch drives are pretty cheap, so I pretty much recommend you get one of these and throw it in there as well, if only because you can buy a USB floppy drive and plug it into a modern computer and then copy files to and from your DOS computer really easily if you don't want to go through all the extra effort of setting up a network stack, stuff like that. And this is the PC I showed early on, and I've been using this for quite a number of years, and basically it's got a 360K drive or 48 track per inch drive and a 3.5-inch drive, and it suited me really well. I've made so many disks on this thing for so many types of systems. It's been really useful and very versatile. Now you might be asking, what about high density disks? And I do occasionally need to read and write those, but I have an IBM PC5170 sitting right there, and it has a high density disk drive in it. So I actually just use that computer. The truth is, these types of high density disks were only used in IBM PC compatibles, and pretty quickly 3.5-inch high density disks replaced these types of disks. So there just don't seem to be a whole lot of these floating around. Don't get me wrong though, I'm not saying that having a 96 track per inch drive is useless. I'm just saying that it seems like many more computers use 48 tracks per inch. So if you have to pick one, I would pick 48. But if you have room to have both in there, then I would actually do that, because there are plenty of other systems besides IBM PCs that do use 96 track per inch disks. And if you don't have that drive, obviously you're not going to be able to read and write that format. Now this is the 96 track per inch drive that I'm going to be using in my new archival PC. And the thing that's really cool about this drive, and it is a TIAC FD-55GFR-633-U. Really long and convoluted model numbers on these. The thing about these TIAC drives, and luckily they're very common and they're also very reliable, is that some of them, and this is one of them, have actual jumpers on the bottom to configure the drive to run at 2 speeds. When 5.25-inch disk drives went from the full height drives, like this 100 track per inch tandem here, down to this half height, they went from a belt drive for the spindle motor down to a brushless induction motor, like this one here. Basically, there's a speed controller on the disk drive, I think it's on this little circuit board right here, that allows it to run at a very precise speed. So there's probably a little Hall effect sensor on the underside of this, and there's coils and stuff. And this thing can lock on exactly to the right speed it needs to run at. This is, of course, different than these types of drives here, which have a drive belt, and they also have a little potentiometer on the back here for adjusting the speed, because this thing uses a much simpler speed control circuit than these newer drives. So because of this more sophisticated speed controller, some of these high-density disk drives, like this one, have a jumper setting that you can set that actually allow it to run at dual speeds. There is a signal that comes across the floppy drive cable, pin 2 typically. The signal, which comes from the floppy drive controller, tells the disk drive, when appropriately configured, hey, I'm trying to read a high-density disk at 500 kilobits per second, which is just like the 8-inch disk format. So the disk drive will in turn run the disk or spin the disk at 360 RPM. When the disk controller on the computer is trying to then read double density or 250 kilobits per second, that signal goes to the disk drive, and when that jumper is set, it will run the disk at exactly 300 RPM. Is having a drive that's dual speed really absolutely necessary? I don't really think it is, because the IBM PC disk controllers support that 300 kilobits per second data rate, which allows it to read and write those 256 kilobit per second disks at the increased 360 RPM. What a 96 track per inch drive like this running at 300 RPM allows you to do is use this drive on an older computer that only supports a data rate of 250 kilobits per second, like a TRS-80 Model 3, for instance. I could plug this drive into there and actually use all 720K on that system with a regular double density disk because of the 80 tracks that this drive supports. Unfortunately, there is no easy way to know if the drive that you have supports that speed change without looking up the manual, and if you can find it, because a lot of these disk drives don't have manuals, and seeing if there's a jumper you can configure to allow that dual speed nature of the drive. I happen to have a Mitsubishi drive here. This is also a 1.2 megabyte 96 track per inch drive, and it also has jumpers and a manual online that I looked up to run this thing in dual speed. And I tested this drive, and it absolutely works perfectly. It runs at a perfect 300 RPM or 360 RPM, depending on the signal going into pin 2 on the drive. So with all of that said, I want to set up a PC that can basically read and write everything that has the MFM or FM encoding. So I'm going to be using this 96 track per inch drive here, dual speed, set up for dual speed. I'm going to be using this 100 track per inch drive here, which always runs at 300 RPM. And I'm going to be using this 48 track per inch drive as well, runs at 300 RPM. All of these in the PC simultaneously, along with a 3.5 inch drive like this, so I can read and write pretty much all of the FM and MFM encoded disks that are out there in a 5.25 inch format and also in the 3.5 inch format. Ultimately, it goes without saying, I'm not going to be able to read and write 8 inch disks, and I'm also not going to be able to read and write the 3 inch disks like the Amstrad uses because, well, I don't have those physical drives hooked up to this computer. Okay, I have done so much talking at this point. Let's build up the computer that holds all these drives. So it's kind of obvious that my idea of putting all of those disk drives into this case isn't going to work. There's just not physically any space. So I have a solution for that. And this is the solution. This is an ATX case versus an AT case like the other one. And as you can see by the front cover here, it has plenty of 5.25 inch drive bays, 4 to be exact, which is actually perfect for the fact that I want to put 2 half-height drives in there, and I want to put a full-height drive in there. It also has 2 exposed 3.5 inch bays. You're probably looking at this and wondering, what are these toggle switches and this rotary knob for? Well, the rotary knob was for a different project, and I'm going to be using the toggle switches on this machine actually. I'll get to that in a little bit. It has nothing to do with the floppy drives. It's just more to adjust the clock speed of the motherboard. I currently have this wire soldered onto it so it can go to the motherboard. But yeah, the 3.5 inch floppy drive will stick through the front, and then of course, all the rest of the drives will be on the top here. As I mentioned, this is an ATX case, and clearly the motherboard that's in that other case is an AT motherboard. I'm not sure if everyone realizes this, but you can actually mount an AT motherboard into an ATX case, and generally the standoffs are all in exactly the right position. Obviously, ATX motherboards extend further up to the top here, and the AT motherboard stops around here, or at least a baby AT motherboard, and the keyboard connector will just stick through the opening on the back of the ATX case here where the normal ports are. For this build, I'm not going to be using the AT motherboard from the other machine. I'm going to be using this one here, the Asus P5A, 200 megahertz MMX, same speed processor that's on the other machine. But this motherboard has the benefit of an AGP slot, which is roughly, if I recall correctly, twice the bandwidth of these old PCI slots. So that's a nice improvement for your video card. I'm glad it has a couple ISA slots though, because I want to be using a Sound Blaster 16 card, and I'm going to need to be using a floppy controller like this one here from TechSelect. Not out yet, sorry about that, but Kevin will have this out soon. I think it's going to be white, it's going to look a little different. But the reason why I want to use this with this motherboard as opposed to the built-in floppy drive controller on the motherboard is because, of course, this has 2 connectors for up to 4 floppy drives. The original floppy drive standard that was invented by Haardt for their first drive supported up to 4 floppy drives, drive select 0, 1, 2, and 3. Originally with the standard, the way you selected which drive was which was by setting jumpers here to select which drive was which, and all of the drives were just connected in parallel to each other. When IBM came up with the original PC5150, they took the floppy drive standard that was the Haardt standard and they changed it up a little by adding this twist into the cable. The twist uses up a couple of the extra wires that were available to select 4 drives originally and made it where one of these cables can only handle up to 2 drives. But the benefit is you set both drives to drive select 1, and depending on where you connect it on the cable, if it's before or after the twist, is what selects which drive you're using. Back to the floppy drive controllers, the fact that there's only 2 drives supported was just a wiring thing, and the actual controller ICs all the way back to the original one used on the IBM PC 5150 drive controller supported 4 drives, in the hardware at least. It's just from a wiring perspective, there was no way to utilize that. And the way Kevin wired up this card, all I need to do is use 2 of these cables, these regular PC compatible cables, select all the drives to drive select 1, have drives 1 and 2 on this connector and drives 2 and 3 on this connector, and then a program like IMD can actually address all 4 of them. Alrighty, with that said, it's time to take apart the other computer, put this motherboard in here, and build this thing up. And I'm going to do a jump cut. There we go. The build is complete. It wasn't too hard to get everything in this computer because it's relatively roomy. Let me show you a close-up of how everything is connected up. Starting from the bottom slot, we have a Sound Blaster 16 CT1740, and this has the, I think it's the ASP chip on there, the Advanced Signal Processor. Attached to the Sound Blaster 16 is a Yamaha XG sound card plugged into the expansion connector there. So for anything that uses MIDI, I can choose to either use the FM synthesis on the Sound Blaster or the XG MIDI capabilities of this Yamaha card. Next up is the Tech Select floppy drive controller, and all 4 drives are connected to it using 2 standard PC ribbon cables with the twist in them. Next up is a compact flash to IDE adapter, and this sticks the compact flash through the back of the computer, and that's the ribbon cable that goes up to the motherboard. Then we have a 10100 PCI Ethernet card. This is an Intel variety. And then lastly, we have an AGP TNT Vanta video card. I gotta say, these NVIDIA TNT cards make really quite good DOS video cards. They seem to support all the various modes for DOS, and they support VESA 3.0 up to, well, 1024 by 768, high color, 32-bit color, and they, of course, are very speedy, being AGP. Next up is the Intel Pentium 200 MHz MMX, and I have overclocked this, which I'll talk about in a second. And then we have this power supply here provided by Big Steve here in Portland. This is a normal ATX power supply, but what's important about this one is it has the -5 and the -12 volt rails on it, which is perfect. I don't know if the Sound Blaster actually needs both of those, but the thing is, this power supply provides them. As is normal for all of my builds, I always take any extra parts from the case, like these are the front bay covers and also some drive rails, and I put them in a bag and stick them inside the case. That way, they don't get lost. Looking at the front of the machine, of course, this computer fits all of the drives. The first drive is the A drive here. This is the 360K or 48 track per inch drive. The B drive is this one, the 3.5 inch disk drive. C is the 1.2 meg drive or the 96 track per inch drive at the top here. And D is the 100 track per inch drive right there. Some of my viewers are probably going to be bugged by the fact that these are not in order, like A through D. Unfortunately, the reason for that is that this case was not designed to ever hold full height disk drives. It actually has these sliding rails which stay integrated, and I had to remove the 2 from this part right here to take this full height drive. And then I tried to put the A drive on the top, but unfortunately it doesn't work because for whatever reason, this drive rail up here, it grips the top set of the screws on the disk drive, and this older 360K or 48 track per inch drive only has screws on the bottom. Let's talk really quickly about how to connect up all 4 drives to this disk drive controller card. We have to keep in mind that since this is only one controller chip, all of the signaling that goes across these wires are all in parallel, except for the drive select signals that go to the drives. Because of that fact that they're all in parallel, drive termination actually does matter. You only want to have 2 terminators, one on the disk drive controller and one on one of the drives. So I removed the termination from the other drives, and this is actually working perfectly. Now, I'm sure lots of people are asking, what's the deal with these toggle switches? For the 2 toggle switches here, what I've done is I've run these to the front side bus jumpers on the motherboard. So when these are both down in this position, the CPU is actually run at 100 megahertz, which is an overclock. With them both in the up position, it's run at 66 megahertz, which is the standard speed. And one of these down is 83 megahertz, and the other one down, the other one up is 75 megahertz. So I have a selection of 4 different front side buses to pick from by moving these switches around. Now the clock generator on this motherboard requires it to be powered off, and then you flip the switches, because if you just switch these while it's running like it is right now, it doesn't actually do anything. So these switches really are just a convenient way to change the overclocking of this CPU without having to open the case up and like move the jumpers around. All right, I have the machine hooked up to the capture device. Let's take a look at how I have this thing configured, so if you try to replicate this yourself, you can do so. I moved the compact flash card from the other computer, so this has a Windows 98 install on it, but I mainly go into DOS. Now I have a boot menu configured, and this comes from Phil's Computer Labs. He's the one who I originally got the boot menu from. I just modified it for my use case. As I had mentioned before, IMD or ImageDisk by Dave Dunfield is the best program to be using for MS-DOS when you're imaging or working with disks from other systems. There's a few things about IMD that you might not have realized if you've ever used this program before. If we go to Drive in the settings, all we can pick from is A or B. What about the other two disk drives that exist on this machine? Well, taking a look at imd.txt, which is the included documentation that comes with it, there are a whole bunch of command line options, as you can see here. And look at the very first one, /4. Assume 4 drives per floppy drive controller. And remember, this TextLite card that I'm using has 1 controller for 4 drives, so that's the option we need. It does also support a second floppy drive controller at a different I/O address, but the thing you have to worry about is that floppy drive controllers on the PC also use DMA channels, and unless you can change the DMA channel, the two controllers may stomp on top of each other. As you can see here, there are a whole bunch of other settings that you can set from the command line. Most of these can be configured in the settings in IMD, but for whatever reason, the number of drives that the program supports can only be set from the command line. There is another important option here that can also only be set from the command line, and it's this one down the bottom, LR or lock data rate. I do have to use that on this machine because of this dual speed disk drive, so I'll talk a little bit more about that in a second. So here in the boot menu, I have 2 options set. One of them is just 4 drives, which basically puts that /4 after IMD, and the other one is force 250 kilobit, which is that lock data rate I just mentioned. And the only time I wouldn't want to force 250 kilobit is if I'm actually reading and writing high density disk drives in either the 96 track per inch drive or the 3.5 inch drive. Since those run at 500 kilobits, I have to enable that setting. But in all other circumstances, if I'm working with disks that are 250 kilobits, the force option is actually appropriate. I'll explain why in a second. First, let's start with this disk right here. I have this formatted on the 100 track per inch drive. So if we slide this into the full height drive, and under settings, we pick D, and we do align, which is going to, and it's just moving the head there, and there it is. The disk is being read properly. Now there's an audible beep that comes out of the speaker in here. It's kind of quiet, so you may not be hearing it. But yeah, this drive is working great. Now if I jump to track 40, there it is. Now it's reading track 40, and let's go to track 70, and there it is, also working perfectly. Now let's take this disk out of here, and let's stick this into the 96 track per inch drive, which is nearly the same as the 100, and they both have 80 tracks. But let's see what happens. So I gotta change this to C, and let's do align disk again. It's reading, but barely. Here's what this is telling us right now. Currently, the 96 track per inch drive is on track 0, and it says that at the very top, track 0, head 0. But the sectors it's reading is not reading all of them. It's only reading 5 of the 9 sectors off the disk, and it's reading them from track 3. Now we're on track 30, and it's currently reading all 9 sectors per track, but it's getting them off track 34, what was written to the disk as track 34. And there we are, track 73 on this drive is reading the disk at track 79. Now think about it, 100 tracks per inch, the tracks are closer together than the 96 track per inch drive. So if you overlay them, when the 96 track per inch drive is on 73, it's actually near the furthest extent of the 100 track per inch drive. Okay, let's try something else. This disk here is formatted just as a normal double density 48 track per inch disk, which is drive A. So I'm just gonna set it to drive A, and let's go to align here, and we should be able to read this disk without any issue. I formatted this in another machine. There it is, track 0 reads track 0, all 9 sectors per track. And here we are reading track 39, and it is reading the disk perfectly. So let's take this disk out, and let's stick it into this 96 track per inch drive. And it should be reading track 0 properly. And it is absolutely reading track 0 properly. Now, if we hit plus to go to track 1, which is track 1 on the drive, it's now reading the disk in between track 0 and track 1. It's still reading track 0, and it's only getting 1 sector. But if we push plus again, now we're on track 2 on the physical drive. It is now reading track 1 on the disk that's in the drive, because of course it was written for 48 track per inch, and now we're running at 96. That's what the whole double step thing is all about. If you're trying to read a 48 track per inch disk in a 96 track per inch drive, if you double step, you're gonna at least be able to read it. Now remember, this drive here is a dual speed drive. So if we exit out of here and we test the RPM, it's going to be running at 300 RPM, which is the correct RPM. It takes a little bit of time to settle, but there it is calculating. It's gonna run the same exact RPM as these other two disk drives. So all three drives, when they're reading 250 kilobits per second, are going to be reading at 300 RPM, which is exactly what I want. But the last disk I want to test is this high density disk here. So let's reboot out of this. And I'm going to pick the 4-drive option without forcing 250 kilobits per second because we need to run this at 500 kilobits per second. So we'll slide this in, pick drive C for the 1.2 megabyte or 96 track per inch drive, and let's do a line. Now at the top you can see it checking the different bits per second, and it's trying 500 and the other ones. Okay, so there it is. It's now reading this high density disk. This is formatted like a normal MS-DOS 1.2 megabyte disk, which has 15 sectors per track, which is why it shows 30 there. Now this is going to be running at 360, or it should be at least. I mean, it has to be because it was reading it. And there it is, it's settling in. There it is, 360 RPM. If we go back to this double density disk here, this is a 48 track per inch one, and we put it in here, remember, we're not forcing 250 kilobits per second right now. And if we go to a line, what's going to happen is it's going to figure out that this is a double density disk. But you see at the top left of the IMD screen there, it's currently set for 300 kilobits per second. That's because at least this version of IMD doesn't understand that this is a dual speed drive. So when this drive is not getting 500 kilobits per second, but it's getting 250 or it's getting 300, it's running at 300 RPM. So it's currently running at the wrong data rate. I needed to read these types of disks, these quad density or double density disks in this drive at 250 kilobits per second. The last piece of the puzzle is getting disk images you download off the internet onto physical disks. The first piece of the puzzle, downloading Dave Dunfield's IMD disk program, which you can just find by Googling ImageDisk and Dave. Dave has some good info right here on modifying a 1.2 megabyte drive like I've done here for the dual speed operation. He probably talks about different jumper settings and whatnot. Here's the download link to ImageDisk 1.19. It's from 2012. And what's really cool is Dave actually has a whole bunch of software and operating system disks in IMD format on his website. So none of these require any type of conversion. You can just download any of these and make them on a machine like this. In fact, I'm going to download the Visual 1050 system disks from Dave here because I actually need to make some disks for a Visual 1050 that I recently got, and I'm working on a video for the future for this machine. And you can see in this archive here, they are all IMD format, which is exactly what we want. I went ahead and I copied one of the disk images onto this 3.5-inch disk from my USB floppy drive. It's actually one of the easiest way to get disk images back and forth. I'm going to run IMD using the 4 drive, and I'm going to force it to 250 kilobits per second. And that's because, of course, I'm going to be using the 96 track per inch drive here, and I need it to write at 250 kilobits per second. I'm just going to double check the settings. So I want to use drive C. That's the 96 track per inch drive. It's 80 tracks. It's 2-sided. I don't know if the original image is 1-sided or 2-sided, but I think 2 is good. And we want to make sure the double step is off because I don't want this thing double stepping each track. We're going to hit W for write. Here's the disk, V1050A. Now you can see this disk image was made back in 2005 using IMD 0.2, so kind of an old version. And while it doesn't mention it here in this description, I happen to know for sure that this disk image is an 80 track or I think a 77 track image, so it needs to have a 96 track per inch drive like this. Now I went ahead and I degaussed this disk and I used one of those bulk tape erasers you can find online. That's because this was written in a 48 track per inch drive, which has those wider tracks, so it could potentially result in some crosstalk. I don't think it really needs to happen, but anytime I switch between a 48 track per inch drive and a 96 track per inch drive with the same physical disk, I do a bulk erase on it. Now you can see it's writing the disk, but it's only writing it single-sided. Now that's because the original drives on that computer must be single-sided 80 track drives, and the drive that's in here is double-sided obviously, but it doesn't really matter because it's only going to use one of the heads. Now it goes without saying, I didn't really mention the double-sided nature of all of these drives. If you go ahead and install single-sided drives on your computer, then all you're going to be able to use, well, are single-sided disk images and read single-sided disks. So I recommend trying to find double-sided drives if you can, although it's not always possible. For like 100 track per inch drives like this, most of the ones I've ever seen, usually Micropolis branded, are only single-sided. Those are going to work perfectly in this case, but you'll just only be able to use single-sided disks. Now, as you can see, it's up around track 55. And that definitely confirms that the disk drives in the original machine are single-sided 80 track drives or 96 track per inch, just like this. It's possible, and I'm not 100% sure, that the drives in the Visual 1050 might be 100 track per inch. And if I find that this disk doesn't work, then I guess I can write it in the other drive here, and maybe that'll work. Now we're going to go to align, and we should see 20, I think, because it's 10 sectors per track. And there it is, it's reading 20. We jump to track 40. There it is, 20 again. No problems. One thing I want to mention about IMD, which makes it so extremely powerful, is if we go into settings and you see the option full analysis yes, what that means is that if you're making an actual disk image, every track, it's going to look to see if the track format has changed on the same physical disk. Normally that's not the case. Most computers use the entire same format across every track on the disk, but there are machines that are a little different. The TRS-80 Model 1 is a good example of that, where track 0, the first track on the disk, is always FM, or single density, and if you have a double density controller in the machine, all of the other tracks are going to be double density. IMD completely supports that. You just have to make sure that full analysis is turned on, so if you're reading a physical disk into a disk image, it notices that one is FM and then it goes to MFM. Now, if you have a physical disk that you want to turn into an IMD disk image, and we're just going to take this visual 1050 disk and turn it back into a file, put that into your system, then you can use this alignment tool to figure out if it's a single-sided disk or not. So there it is reading track 0. If I push the H key, it's now showing question marks because it's reading head 1, the other side of the disk, and that's blank. So that just confirms this is a single-sided disk. We're going to go up to track 70. I want to see how many tracks are actually on this disk. So you can see it's reading track 79, which is actually track 80, because the starting track, at least in here, is 0. That alignment option in the main menu there is absolutely essential to help you figure out exactly the disk format of the disk you're about to image. How many tracks, how many sides, and even the original tracks per inch of the drive that was used to make the disk. So we need to make sure we configure the settings properly for making this disk image. We're going to set it to 80 cylinders, which is 0 through 79 for the track numbers. We're going to pick one side, because if we pick double-sided, it's going to read the other side of the disk, which is blank right now, and you don't want that. We're going to make sure the double step is off, because this drive needs to read every single track, not every other track, and the rest of this stuff we're going to leave as it is. And then we're going to push R for read into file, and I'm going to say test.imd, and then here's a box you can type a little bit of a description. So we're going to say visual 1050 disk test, hit escape, and push enter, and now it's going to analyze the disk. And remember, I have it forced at 250 kilobits per second right now because I have to do that for this dual speed drive. And there it goes. It's reading the disk right now, and you see it says 10 sectors, 512 bytes, which is exactly what we would expect, 250 kilobits per second. Notice as it reads the disk here, it has an R and then an A, and the A is the analysis part, and that's because I have full analysis turned on. If it was turned off, then it would do the analysis once at the beginning, and it would read the rest of the disk without doing any further analysis. It goes faster, but I like to keep that option on in case there's any weird disk format changes of the disk that I'm reading that I'm maybe not aware of. And there we go, it completed. It says 800 sectors and 153 are compressed. I think that means because those sectors are mainly empty, and just to save space in the disk image you created, actually compresses those sectors. Also, sometimes when it makes the disk image, it might say deleted data. I've found that that's not generally a problem, although I recommend reading through the documentation on IMD if you want to know more about what that actually means. The final piece of software that's pretty invaluable for manipulating disk images that you download that you then want to write onto physical disks is the HXC floppy drive software. And HXC 2001, this is a floppy drive emulator, and the software that goes with it, which is this HXC floppy emulator software right here, is incredibly useful for manipulating disk images because of the wide range of disk formats that it supports. Let's load that visual 1050 IMD file that we just wrote onto this disk here into this software. Now this loads up right away, and it tells us right here it's 80 tracks and one side. So that also gives us an indicator of what kind of drive we're going to need to write this disk. Some awesome things this can do is we can load up the track analyzer. Now I happen to know that this is an MFM disk, and if we hover over these, you see it actually shows the breakdown, and I'm trying to get over there, it shows the breakdown of the MFM sector. Now that's kind of how, when IMD is doing the alignment function, that it knows that it's reading sectors from the wrong track if you're using a physically different drive. And that's because the sector itself actually contains that track information. But you can see the data that's actually contained in the sector right there. But even cooler is we can change the visualization to a 96 track per inch visualization, and there is the physical layout of the tracks on this disk. Now visual 1050 disks have 10 sectors per track, and that's what IMD was telling us. And we can see that visualization right here, along with the gaps that exist in between each track. Now, nothing we're seeing in this utility yet are particularly useful, but what is very useful is the ability for this thing to load and then save disk images into different formats. In this directory, I have the actual stream files, which were made with the CryoFlux archiving system of the Mercure XR4 Ti Ford car disk. It was basically a demonstration disk that they'd give you at the dealer to take home, and you could look at all the specs of all the Ford cars. And as I mentioned at the beginning of this video, with these stream files, you can only really write them back to a disk using something like the CryoFlux or the Grease Weasel. But you can actually open them in this utility, and then we can save them back as an IMD file. So there it is, it just loaded it up. 40 tracks, 2 sides. Let's look at the track analyzer. There's the actual stream data that was read off this disk. Now, if any of these sectors were bad because the original disk was failing or the drive was failing that I used to archive it, you'd see all sorts of red marks in here. And that's a really good indicator that your disk image that you made, at least with those stream files, which remember is the actual flux information, has a problem. With the stream file loaded into this utility, I can now say export disk or save as. One of the formats that this supports reading and writing to is IMD right there. And if we pick this and let's save this as XR4 Ti, I'll just copy the IMD disk image here to the A drive on my USB drive. I copied the file onto the hard drive here. Let's write this onto a physical disk. There is XR4 Ti. I pop the disk in there and let's hit enter. And this should write this to the disk. The HXC floppy utility is extremely versatile for getting disk images for other systems. So here are some TRS-80 Model 1 disk images. And I downloaded the file and it's in a .dsk format, which I think is used by one of the TRS-80 emulators. I'm not actually sure exactly how many formats the HXC utility loads, but it seems to be very comprehensive at figuring out what things are. So if we load this, and it says it's an 80-track one-sided disk, which doesn't really make sense. Let's go to the analyzer. And it's not actually able to make heads or tail of this disk image here. Like none of the data is decoding. Oh wait, maybe it's FM. Oh wait, there we go. Okay, it is FM. And actually taking a look at all these disk images right here, blank disk, 80 track, single-sided. So I guess for whatever reason, these disk images were all created on a computer that was using an 80 track or 96 track per inch drive. So these aren't ideal because most people are gonna have 48 track per inch drives on their TRS-80, Model 1, Model 3, stuff like that. So you have to find the 48 track per inch or 40 track disk images and write those to physical disks. I spent so much time at the beginning of this video talking about all these physical differences with the different disk formats so that when you download these disk images, you can try to make heads or tails of what you're downloading so that you know you're getting an appropriate disk image that is hopefully gonna work on the end system you wanna run it on. Let's grab another Model 1 disk image off a different site here. So this is LDOS 531. I can see that these are also .dsk files. And there it is, 35 tracks, 1 sides. That is the appropriate size for the original disk drive that was on the Model 1. It was only a 35 track drive. Well, it had 0 through 34, and that's because physically it just wouldn't go any further past 35. Of course, if you're using a 40 track drive on there, no problem. They're both 48 track per inch. It's just that a lot of the disk images for the original system are gonna be 35 like this. Let's take a look at the visualization, and there we go. We can see that this is entirely an FM disk image, which is understandable. The original disk controller for the Model 1 was only FM. Later ones supported double-sided and MFM. And then at this point, all we need to do is export this, save it as an IMD disk image, load it on this computer here, and then it would actually write the image with no problem. So there we go. I think I'm gonna end this video here. I know it's been very long and there's a ton of information in here. I really tried to pack it in. I think it's gonna edit together into something that's gonna be pretty long, but I hope there's a lot of useful information. And if you're trying to make physical disk images for your old computers, or you're trying to take disks and turn them into disk images so you can archive them, upload them to archive.org or share them, that this video will prove very useful. I've had to leave out quite a bit of extra detail in this video because there's just so much more going on with disk drives, but I think there should be enough basics in here to get people started with this process. Let me know in the comment section if you have questions and I'll try to answer them and maybe do some clarifications. Check the pinned comment that I'll have at the top of the comment section if there's any information that I'm gonna need to add that I forgot to put in this video and that's critical, I'll definitely put it in there, or maybe I'll put some questions and answers in there as well. So yeah, definitely check that out. I tend to do that on all my videos just as a way to add updates after the fact. So if you liked this video, I'd appreciate a thumbs up. If you didn't, you know what to do. Hit that subscribe button if you haven't already. Huge thanks to my patrons. Their names are going up the side of the screen here. They get early access to videos, behind the scenes, stuff like that. And I guess that is gonna be that. Stay healthy, stay safe. I will see you next time. Bye.